Okay, so next speaker this morning is Heggie from Edinburgh. I think he's going to talk about globular clusters. So let's go ahead as soon as you're ready there. Fire away.
Okay, well, it's going to be very hard to follow Doug's lead at the beginning, but I must correct one thing he said. I have to exculpate Scott from the suggestion that Doug was nominated for the opening lecture by Scott. I think it was actually originally me that's to blame, Doug. So, you can get your own back now. So I want to thank Doug for the invitation to come here, and Pascal and all the other organisers for making the arrangements. Pascal signed herself in an email as the General ISIMA Dog's Body, which I think gave me a lot of sympathy for her, and it's all working out very well now. One thing she couldn't change was the national holiday. So what I want to do is to talk about, this is a course about modelling, but I also want to try and insist on understanding the models as well as just being able to do the models. And I've divided this set of 3 lectures into more or less 3 slightly unequal parts, one of which is just a little gentle introduction to globular clusters, pretending that you've never seen them before. Then I want to talk about something which I call snapshot modeling, which is not particularly what I've been doing most of my career, but it's a very important aspect, especially from the point of view of upcoming observational programs. And that'll take me somewhat less than my first hour and a half. And then I want to talk about evolutionary modeling, more or less from the point of view of theory, with the minimal application of computer simulation, although I'll illustrate one or two of these theoretical issues with the results of simulation. And then at the very end, probably the third lecture, which I think is on Wednesday, will be largely about numerical methods for studying the dynamical evolution of globular star clusters, especially globular star clusters. I'll say almost nothing about open star clusters. I think they've kind of been done by the community now, which is of course ridiculous, but nevertheless they're not receiving the attention they really deserve. So, an introduction to globular clusters. Why should one study globular clusters? And there are 2 kinds of reasons. First of all, the reasons which you put in the sort of hard-nosed reasons which you put in your research proposals. You know, you have to study globular clusters because they can tell you about the formation of galaxies. If you're interested in millisecond pulsars, the globular clusters can tell you something special. Similarly, if you're doing stellar evolution. All of these, many areas of astrophysics, the globular clusters tell you something special. And then there's the reasons which you can't put in a research proposal, like the community is full of very nice people. And they've been some of my best friends for the last 30 or 40 years, and I love the community. The second thing is that the clusters are very beautiful. As you can see, this is actually an amateur image of 47 Tucani, which has already been mentioned by Doug, and you can always recognize 47 Tucani because out here is a small Magellanic Cloud, and even if you see an all-sky picture, and if you can pick out the small Magellanic Cloud, you can see a globular cluster because it's the bright dot right beside the small Magellanic Cloud. And in most ways, it's fairly typical of the galactic globular clusters. It's nearly spherical, it's very old, and it's one of over 100, about 150 in the Milky Way. There are new ones being discovered every few years. They range in size from a few thousand stars, that's N, to a few million stars. This is probably around about 2 million stars, I think. Their typical sizes are a few parsecs, and in places they seem to have incredibly high stellar densities, something like 1 million solar masses per cubic parsec. But, there was one thing which I also wanted to say about the globular clusters. They look very simple. They look just like an array of dots attracting each other gravitationally. And of course, and in fact, 40 years ago, when I started working in this subject, that's how simple they were. So you could be an applied mathematician or something like that, and you could still do globular clusters that really you can't very easily nowadays, and you have to be a theoretical astrophysicist, because all of these things are involved. Not only the gravitational dynamics, which attracted me in the first instance, but also the formation of stars, the evolution of the stars, and even collisions between the stars. That's something which you need to be able to model because of the high stellar densities. And it's one of the things which makes these clusters very interesting. Star formation I'm going to have very, very little to say about, because I'm going to focus on the globular clusters, which are old and don't really form stars anymore, except by collisions, for example. But if you're studying young, rich star clusters, which will be the issue of some of the projects which I'll be talking about, that's something you do have to worry about. It used to be thought that all of the stars in a globular cluster would form in one little bang, but in fact it seems likely that, as Doug mentioned a few minutes ago, that there's more than one early phase of star formation. But after about 100 million years, the star formation is essentially finished. I mean, that's still the paradigm. This is good n-body dynamics because the star diameters are very much less than their separation usually, except obviously in collisions. We do have to worry about external matter. Again, I've got projects which are deeply involved with the role of external matter, and you do have to worry about stellar evolution, including the evolution of binary stars. The very big worrying thing is if you do have a collision between two stars in the star cluster, how do you evolve the collision product? Because that's a very non-standard kind of problem in stellar evolution. And there are aspects of the stellar evolution, especially involving even orbit binary stars, which are rather imperfectly understood. And the globular clusters are a great locus for trying to establish observational facts about that. Now, to focus on the dynamics just a little bit, this is a kind of summary of probably my second lecture. Because I'll be talking about the different ways in which the dynamics can be formulated. Obviously, there's the n-body equations, those equations which have an appealing but deceptive simplicity, as Lyman Spitzer once said. That's the n-body equations. I've also grouped Monte Carlo descriptions amongst n-body formulations. They're the next best thing to n-body formulations, but they're better than n-body in some sense because you can do them in a few days instead of a few thousand years. Then there are phase-space descriptions, statistical descriptions, starting with the collision-Boltzmann equation. See this old paper by Michel Lennon to find out why the name is there. The Fokker-Planck equation, which Doug mentioned to some extent, which I'll deal with in some detail, again based on the work of Lennon mainly. And then there are two fluid descriptions in which you basically regard a star cluster as being a big star, except that the atoms of the star are the point masses made by the individual stars in the system. And then there are scaling descriptions, and I'm going to say a bit about one modern scaling description from Mark Hillis and his students at some point in the talk. I promise I'll try not to flash this in the direction of viewers ever again. I was going to point out Mark, but then I realized I was just about to blind him, so snapshot modeling. This is a kind of non-standard term for actually what is the bulk of the modeling of globular clusters, which takes place not just now, but in previous decades. You don't really care how the globular cluster got there, what's going to happen to it in the future. You just want a model of the distribution of the stars and their kinematics and their dynamics as it is now, and consistent with the observations which we take with telescopes now. And actually, it's interesting that this kind of modeling has tended to be done by people who don't work in globular clusters. You know, they come from the elliptic galaxy field, for example, and apply the tools which have been developed there, which is all to the good. And I'll mention some of these tools later on. And I do emphasize the importance of this kind of modeling. simply because of the wealth of observational data which is promised by things like Gaia. Mark again has a thing called the Gaia Challenge, in which he's trying to assemble a sort of suite of tools for analyzing the Gaia data in the context of star clusters, for example. And the basis of some of these tools is what I'll be talking about. But the earliest tool that I want to talk about, which goes back to Ivan King in his early days, 50 odd years ago, is a thing which I'll call the King template. Because it's not really a model in the sense that most of us understand for models. It's just a kind of figure of best fit, as it were, of something about the star cluster. But it's been very important, and modifications of this are still important. This is basically a formula for the surface brightness as a function of distance from the center of the star cluster. And there are three constants in here, RT, RC, and K. And there's a famous dictum by Enrico Fermi, give me three parameters and I'll fit an elephant. And basically with these three parameters and this formula, you can fit a globular cluster to a large extent. Here's an example down here. Our measurements of the globular cluster, MC505CS. And so this is the surface brightness, or the logarithm of the surface brightness here. This is the logarithm of the distance from the cluster center. We assume spherical symmetry here, obviously. There's a sort of flat region here where the surface density is almost constant. And then that begins to fall off with a radius, which is called the core radius. Complicated kind of concept. This got several different definitions. But anyway, this is called the core radius for the moment. And then there's a kind of cutoff radius, which again has got sort of complicated connotations of the origin of this name. It's often called the tidal radius because of a particular interpretation of that cutoff radius, but it's not necessarily a correct interpretation all the time. And then in the middle, somewhere not shown here, is half-mass radius, which is another sort of standard radius for measuring the size of these objects. It's the radius of I shouldn't say this, it's the radius of a sphere containing the central half of the mass, but in this context, it's often applied to what would be called the half-light radius, which is the radius of a disk containing the which contains the central half of the total light of the star cluster. So all of these things will get mentioned from time to time. And there's a great compendium of some of this kind of data in a slightly condensed form in the famous Harris catalog, which you'll see referred to there. Okay, now if you fit a King template to a star cluster, it will tell you nothing about the velocities of the stars in that object. And to do something like that, that is to link the spatial distribution of the stars with the velocity information about the cluster, you've got to do something a little bit better. That's what you're in line for. You've got to do something a bit better. You've got to link the positional data and the velocity data. So instead of having a distribution just of position, you have to have a distribution of both position and velocity, because the dynamics is done in terms of the acceleration, which always requires initial data about the velocity and the position. That's the fundamental issue. So you assume there is a one-particle distribution function in phase space, which I'll again call F. It gives rise to a smooth density distribution in configuration space. I'm here assuming that all the particles have the same mass, which, by the way, is an issue with almost all of this snapshot modeling, especially the sort of more modern variants of the snapshot modeling. And again, we've got projects for ISIMA, which are concerned with trying to put the multi-mass back into some of the more advanced kinds of models. Anyway, from the data, you can find a smooth potential by Poisson's equation. There's an evolution equation, which is essentially conservation of number density in phase space. This is basically df by dt plus the divergence of a velocity times the gradient of f, except it simplifies just a little bit because of the eccentricities of the rate of change of V and rate of change of velocity. Now this is an equation which can be, my wife's appeared on one. This is, okay, yes, the solution to this equation is something which you can find discussed at length in Scott's book with James Binney, which will be a general sort of underlying text for almost all that I've got to say. And there's an important class of self-consistent models, that is models whose distribution function gives rise to the potential, which also appears in the evolution equation. And these are based on integrals of motion in assumed spherically symmetric system, which are the angular momentum, the magnitude of angular momentum, and also the energy per particle, or per unit mass actually, which involves the potential, which is assumed to be time independent. And then there's this Jean's theorem, which you can find discussed in Tremaine, which at least tells you a whole swathe of solutions of the Boltzmann equation. And the most important of these still, I think, is King's distribution going back to 1966. So it's different from the King template, which really is a self-consistent model, and its variants of the King paradigm, which have sort of set the running in this field ever since. I'm going to go up some water in due course. I can probably do it. Okay. Thank you very much. Yeah, I was used all my career to just shouting to the back of the lecture theatre, which is about 3 or 4 times the size of this when I was in full-time employment. But now that I'm retired, I found my voice was gradually not up to it, and I can't shout as much as Dr. So I'll need a little bit of reinforcement from time to time, but water is good enough. Okay, so again, there are 3 parameters here. This constant in the front here, this constant sigma squared, and also an unseen constant here, which is the value of the central potential, because by convention, the edge of the King model is taken at the place where the potential is 0. And it's for that reason that it's only for negative energies that one actually has a non-zero distribution of stars, and for positive energies you regard it as being outside the star cluster with the escape, and so the phase space density is 0. And so you get a whole suite of these models. There are, as I say, 3 parameters, but 2 of these have been taken out in this diagram, which shows the space density as a function of the distance from the center, and also the projected density or the surface density as a function of distance from the center, taken from Tremaine. So the central surface density has been normalized to 1, this is the logarithm here, and also the core radius essentially has been normalized to 1. So that leaves only a 1-parameter family of models, and here are 4 models from this infinite family of models. There's varying concentration. This is a low concentration distribution. This is a high concentration distribution. Fitted for some reason to what must be some galaxy somewhere. I don't know why people do this, but anyway, there was a book on galactic dynamics, so you were excused from fitting a galaxy. And Ivan did this himself in 1966. So these models do get fitted 60 years or 50 years later to star clusters. Here's an example from Alisoki's work just a couple of years ago. And more or less the point about this thing is that this is the one model you can try and fit both the surface brightness here. This is surface brightness rather than surface density there in mind. And you can also fit the velocity dispersion profile, or at least you can try. You see it doesn't quite work for the surface brightness near the middle. As far as the observational errors are concerned, this is good enough for the cluster dispersion profile. Something which you'll also learn from being in Tremaine is steady-state virial theorem, which connects the kinetic energy and the potential energy of one of these systems. I can't remember what footnote 2 is here. It's off the bottom of the page. It doesn't matter. I'll try and put these slides up on the some website somewhere. If it doesn't go on the ISIMA website, I'll certainly do it on my own website. Probably by the time I finish the last lecture, just in case I change my mind about anything, which will be after Wednesday. So if it doesn't appear on my professional site after Wednesday, please shout and I'll try and do something about it. Maybe it's a local site. Okay. So what this implies, the virial theorem, which is true not just for the King model, but for any self-consistent model with the assumptions which I've already introduced for King, is a relationship between the typical stellar speeds and something which I've simply referred to here as R, which I'll specify in a bit more detail later on, but generally speaking, the mass and the size and the velocity dispersion of a star cluster in virial equilibrium or in self-consistent fusion self-equilibrium is related by something in this form. There's another model which is beloved by theorists for no better reason than that they can write down the solution almost from memory. This is Plummer's model, and I've jammed it in here simply because it's another example of a self-consistent model, but it's really, amazingly observant to do that to fit this thing. Nevertheless, it's primarily a theorist's placing, and it's used for initial conditions. And you might equally well ask, well, why did theorists choose this as initial conditions? Because as sure as guns, the initial conditions of a star cluster is nothing like this. But never mind. So the density is a nice thing here, the potential is a nice thing, and velocity distribution at any radius is given by a power law. And then there are certain beloved theorists' units, which used to be called n-body units. I like to call them Henon units now, after Michel Henon, who died last year, and certainly deserve to be credited and commemorated for the invention of these widely used units, in which the constant of gravitation is 1, total mass of your system is 1, and then there's an issue concerning how the radial scale is specified. Okay, now if you, like the King model or the Plummer model, use a distribution function which depends only on the energy, since the energy only depends on the magnitude of the velocity, if you go to a certain point in one of these models and look all around you, the stars which are moving in different directions are all moving with the same mean square speed. So it's an isotropic distribution of velocities at one point in space. And we're getting to know now, and it's kind of been obvious from common sense for a long time, that's not how star clusters will be. And there are various schemes for constructing anisotropic generalizations of the King model, which can be done by introducing a distribution function which depends not only on E, rather than sort of King style, but also on the angular momentum. So if you've got a high angular momentum star, which means one in a nearly circular orbit, its probability is diminished exponentially according to this factor here. But it turns out that if you do it with a factor of this kind, the cluster is rather isotropic near the center, which again makes good qualitative sense because there's a lot of interactions going on there, and becomes more anisotropic towards the outside, which again used to be thought of as being a sensible way of setting things up, but it's not actually. And again, I've got projects which are involved with trying to find out exactly what the distribution of speed should be chosen to be towards the outside of a star cluster. So anyway, this introduces a fourth parameter, so you can fit lots and lots of things with this. I think it goes back to Michi, actually, this is a paper in which you can find the model described in some detail. Then there's another issue which I touched on, which is how to add the obvious fact. There's again a fact that's been obvious for a long time that different stars have different masses in globular clusters. How do you insert this into one of these models? Well, the physically best justified way of doing this at present, I think, is still the one which is applied to the King model, which says that deep inside the potential well of the cluster, where this is a huge term and it beats out the other -1 which appears in the King distribution, you'll see that the velocity dispersion, because this is a distribution of velocities which is Maxwellian. Maxwell was born in Edinburgh, by the way. Famous Scottish physicist. So this is a Maxwellian distribution, and the one-dimensional dispersion is sigma. And if you try and argue again on physical basis that equipartition of kinetic energies may be approached deep in the potential well, because certainly if you're well out in the potential well, escape is going to modify this. You might imagine that there's going to be approximate equipartition of kinetic energies, which would mean that for two species, 1 and 2, there should be this relationship between their mass and their velocity dispersion. And you can accomplish that if you choose a distribution function for the ith species in which the mass of the ith species appears as a coefficient in this exponential term. And that gives you approximate equipartition for when you're deep down in the potential well of the star cluster. Trouble is, nobody really knows how to do this kind of thing for non-Maxwellian-like distribution function. Now, you may wonder why we ever choose a non-Maxwellian-like distribution function for a very, very old star cluster, which has been colliding gravitationally for a Hubble time. But the question does arise because there are plenty of clusters with rather weak collisions between gravitational encounters between stars, and so this becomes an issue. And again, we've got a project which is involved with how to try and improve that. But here's an example of what happens if you try and do one of these multi-mass King models. This is described in an expository fashion in a pioneering paper by James Brown and Roger Griffin. By the way, you'll see I take the long view in this subject. I mean, I've given you papers from the 1960s and now the 1970s. It's really like when you teach mathematics. You don't start with sort of 20th century mathematics. You start with 17th century mathematics, and then you gradually work your way through to the present day. So I have to do much the same with these expository talks on globular cluster dynamics. Okay, so what they did here was have a model constructed just for illustration of 3 species of mass 1.5, like neutron stars, for example, mass 1.0, like very white dwarfs, for example, and 0.1. I think they changed their mind and made it called just 0.5, like the sort of average main sequence star in an old globular cluster. And what you'll see is that the heavy species, the neutron stars, are very centrally concentrated. I mean, this is a log of projected density here. So these are 2 or 3 orders of magnitude below the bright stars, and out of even here at the core radius, actually. Inside the core, they still don't dominate, but at least they're much more abundant in the core than outside. Whereas the lowest mass species, the average main sequence star, is the one which dominates more and more as you go towards the outside of the star cluster, which makes a good deal of sense, consistent with quite a lot of observational data in which one can actually count stars of different masses. And what's happened here is that what started with equipartition of energies is turned into segregation of masses. So the heavy masses are segregated in the middle, and the light masses get segregated towards the outside. In more naive audiences than this, I say that this is the opposite of what happens to your breakfast cereal. You know, you shake the box of the breakfast cereal, and all the small particles go to the bottom, and all the heavy particles, the big particles, go to the top. It's upside down for some reason in self-gravity system. Now rotation. I don't know if Dave Merritt, no, he's writing his lectures actually. He decided he knows all this stuff, I think, and which is a pity because this is one slide from a paper by Dave, which I was going to show. This is the big globular cluster Omega Centauri. This paper with these two other observers. And each dot here is a star in Omega Centauri for which these guys, Newman and Mayor, observed radial line of sight velocities. And what Dave did was to come along with a non-parametric model, which was basically a way of extracting a smooth sort of rotation profile. Not even a rotation profile, it's a rotation map, actually, for Omega Centauri from this data. And it's very, very vivid that you can see one half of the cluster approaching you, and the other half of the cluster going away from you, or maybe the other way around. So this is a rotating cluster, and what's been done here is to map the rotation without any assumption on the functional form of the rotation, except that it's smooth. And if you talk to Dave, he'll try and convince you that this is the only way to do this kind of modeling, actually. You shouldn't use parametric models of star clusters. You should use non-parametric models. Well, you're going to have that argument with him. But there's one aspect of this game which I wanted to mention here because, as I said, a lot of the people who work on the kinematics of globular clusters come from different stellar dynamics, which is the dynamics of, for example, elliptical galaxies, where it's become common to emphasize the importance or unimportance of rotation in terms of the V over sigma ratio, which is, well, there are issues with what I mean by this V here, but it's basically the rotation velocity divided by the dispersion of the random velocities of the stars in the star clusters. So V upon sigma is something which is commonly seen. Anyway, going back to the thoroughly parametric models, how does one add rotation to one of these models? And here's an example which has been applied by somebody in this room, actually, to globular cluster fairly recently. I did say that observers do fit tunnel models to globular clusters, and I said that there seems to be a very good reason for that, but this particular set of authors that I have in mind also applied one of these models to the same globular cluster, and makes it really more sense. So if a cluster is in rotation, you might imagine that it's somewhat oblate, and if it's axisymmetric, then one still has an integral of motion, which is the component of angular velocity, so angular momentum, about the z-axis, the axis of rotation, and you can construct solutions of the Collision-Boltzmann equation with distribution functions of this form. It's not very easy to do because the solution for the potential is not nearly as easy as it is for a spherically symmetric cluster, but it was done by Annalisa Bai, who's coming here next week actually as part of the faculty team for ISIMA. She's my postdoc at the moment, I'll say a bit more about her this afternoon. Her supervisor, and she devised a system of models of this kind, and you can see a bit of a plethora of parameters in here. I think I've got one or two of these things a bit messed up. By the way, if you find some typos in my slides, please tell me, and you'll get extra credits in the end of the week examination for the 3 lecture series. They all students are going to sit an examination on Friday before they get let out for the weekend, and you get extra credit if you spot some mistakes in our slides. So this was the choice of distribution function which they made. You can see that it's got certain elements of kings in it, except instead of involving the energy, it involves this combination of 2 integrals, which is the self-integral, which we call I. And also there's another subtlety about the degree of smoothness of the joining of the distribution function where I is equal to 0 onto the outside of the cluster, that is the range beyond the edge of the cluster. Depending on one's choice of these parameters, one gets, this is a cross-section of the density map of one of these models. So this is the axis of rotation here, and we're going to show one half of it. This is a meridional plane. And for small rotation, this route is dimpled, which is a slightly odd feature of these models, but nevertheless very nearly spherically symmetric. And then as the rotation increases, one actually produces this very interesting sort of toroidal distribution of density near the middle of the model. Now this is something which is again going to be the focus of some of the projects which Annalisa and I are going to be dealing with, I hope. That the dynamical evolution of something which has an initial density distribution which is as toroidal as this is quite an unknown area of the subject, and a very interesting one. Because even though one might never see a cluster which looks like this now, it may nevertheless give you signatures in the structure of the cluster now, which is worth exploring. Okay, now I'm going to deal with this topic in a little bit more detail, again because, well, this is an area which is rather close to my own heart, I must say. Since there are going to be one or two projects which are concerned with the effect of the galaxy as a whole on a little cluster which is going around it, since there are going to be such projects, and one of them actually starts with a bit of theory which develops a bit of theory which I'm going to be doing now. I'm going to be doing this bit of theory with a little bit of care, just to set the scene. So this is again a model which has got elements of realism and fantasy. This is a cluster which is on a circular galactic orbit. Nobody's ever found a globular cluster which is on a circular galactic orbit. And in fact, one of the projects is how to understand these same phenomena with elliptic cluster orbits around the galaxy, which is an unknown area, an important one. So how does one do a problem like this? Let R be the position vector of the center of the star cluster. There it is, relative to the galactic center. And I'd really better start getting on to pictures on the blackboard just to summarize this. So there's the galactic center. There's the position vector of the center of the star cluster. And if you've got a star out of the star cluster, there its position vector relative to the center of the star cluster is going to be little r. Now, I haven't very carefully defined what I mean by the center of the star cluster here, but it'll be implicit in what follows. Furthermore, I'm going to use a system of coordinates, and I always wish I'd put this arrow going in the opposite direction here because it seems just a little bit back to front to me. But the system of coordinates is going to be such that x is out there. Let me just do it the other way around just to keep our wits about us. And imagine that the cluster is moving right there, and the y-axis is in the line of motion of the cluster center at the instant when it's at that particular location. Okay, so the position of the star relative to the galactic center is the sum of these two radii here. The sum of these two vectors. The velocity of the star relative to the galactic center is just the time derivative of this vector. Now you have to watch because these vectors are going to be represented in a rotating frame of reference, which is also accelerating. And that means that when you work out the total derivative of this thing, you've got to take into account not only the rate of change of the coordinates of the cluster center and of the star relative to this rotating axis, but you've also got to take into account the velocity contributed by the rotation of the axis themselves. And that's what this term here is. It's just the cross product of the vector angular velocity which is out of the blackboard here into the screen on the other picture. And then you've got to add the time derivative of the coordinates of these vectors in these axes. And actually the coordinates of this vector in these axes is constant. Something which goes back to something which Bob mentioned. So when you work out the acceleration, you have to do the double derivative to this, which means you have to take omega across all of this, which is just like doing omega across r plus r here. And then you have to add on the time derivative of the various bits of this, which only affects r and affects r dot, which gives rise to these two terms down here. So when you look at this, there are two terms like this, which give rise to the Coriolis acceleration. This is the acceleration in the rotating accelerating frame, and this is now the rotation frame. Now the equation of motion, going back to Newton, says that this acceleration must be equal to the total force divided by the mass, which is the negative gradient of the total potential acting on this star. There are two contributions here. One is from the galactic potential, which is UG. One is from the cluster center, which is this U here. And so the equations of motion now boil down to this pair of terms at the end here. So that we've reproduced at the top of this screen here. That's as far as we've got. By the way, there's already an approximation involved in there. I wonder if anybody spotted it. And that is the approximation that the center of the galaxy is the origin of an inertial frame in which we can use Newton's equations of motion. I mean, people have got this kind of thing slightly wrong in details in the past, and you usually don't have to worry about it, but sometimes you do. Okay, so here we go. Similarly to the cluster obeys the same equation of motion, except with little r equal to 0 and no cluster potential. It doesn't kill itself. And so one just has this term here, the omega plus r, and the galactic potential, which gives rise to this thing here. And if you subtract these two equations, and I'm going to have to go low tech now, I think, because my laser didn't work. If you subtract these two equations, this bit here goes away, quite a lot of this goes away, or it's still here, but it has to be dealt with, and so you get this equation for the evolution of the position vector of the star relative to the cluster center in terms of all the various potential. And then you do a Taylor kind of approximation or expansion of the galactic potential, because you imagine that the star cluster is very small in size compared to the distance to the galactic center. This produces this sort of vector form of the Taylor expansion to the lowest order, well, next to the lowest order, because the lowest order is actually just going to cancel this term here. And then there's a bit of working, which I don't really know if I should bore you with. This is a boring lecture in two ways, by the way. And it's boring because there is some detail which is boring, but one just has to do it. And if you're doing this project, you have to do this in a bit more. And so I hope if you like this kind of thing, you're going to like that project, at least to begin with. So anyway, you want us to simplify this a little bit, and you can expand this vector triple product. Let's assume that the galactic potential is spherically symmetric, so it depends only on the magnitude of the position vector r, and then the gradient of this is just the ordinary derivative of the vector potential in the direction of the unit vector in the radial direction. And then you can work out what this is in terms of the equation of motion for the star cluster, or the center of the star cluster. Gravity is only the square times the vector r. And then this thing here, you can obtain by, there's a bit of sleight of hand when you're going from here to here. And you have to be a little bit adept at doing this kind of calculation in order to do it without doing some intermediate steps. But it does lead to a very simple form for this seemingly rather obtrusely object here. And at the end of the day, what one gets is something a good deal simpler, that this mess here, plus this term here, the sum of these two terms actually gives rise to something which is relatively simple. And so this is as far as we've got now. This is what came from the Taylor expansion stuff which I was just doing. And this is all that's left of the galactic potential, and there's a bit of centrifugal acceleration here. There's the Coriolis acceleration here, and then there's the cluster potential gradient over here. And then to work with these, one eventually has to go to the actual coordinates, x, y, and z in this frame here, in which these vectors have very, very simple forms. The angular velocity vector is only in the z direction out of the blackboard, and so this is the what you get. I must say this was the first time in my life I've ever arrived at this expression here. Because I often have to write down these equations from memory, and I always get stuck at this term here. Because I always think of this in terms of omega squared, a thing called the epicyclic frequency. And I can never quite remember how the epicyclic frequency boils down in terms of galactic potentials and things like that. But it turns out that the combination of omega and the epicyclic frequency that you need in this problem is this very, very simple thing here. I recommend that to you just to think about that. For example, if you have a point mass galaxy model, the angular velocity is given by this kind of familiar Keplerian sort of formula. And so if you work out the derivative here, this cools down a -3/2 factor because of the r to the -3/2, which is implicit in this formula here. That turns as 2 into a -3, and you basically end up -3 omega squared. So you get a 3 there for an approximation of the galaxy potential as being a quantum mass potential. If it's an isothermal galaxy in which the potential is logarithmic, you get another 3 here, but a -2, and so on and so on. So you get these three equations. And it turns out, again, as Doug mentioned, that there is an energy integral. And I'm afraid I'll often call this the energy integral for this problem, because kind of in mathematical terms, that's what it is, even if it's not the energy in any kind of inertial frame. And it is related to the Jacobi, essentially the same as the Jacobi constant that Doug also mentioned. But the Jacobi constant actually differs from this by a factor of -2. Which is a real nuisance, but it'll come out in some later things that I'll see. So anyway, there's this constant of the motion. It's the energy in the rotating frame, and it consists of a kinetic piece, the potential of the cluster, and then this piece here, which is a combination of galactic tidal field and centrifugal potential. And I say it's more correctly called the Jacobi integral, but it's not more correctly called the Jacobi integral because of that factor of -2. But it's a very, very important integral. And the trouble is you don't have that integral if the assumptions of this derivation aren't there. If the orbit of the cluster is elliptical in particular, nothing in here actually pulls through. You do get equations like this, but they're a good deal more complicated. They're time dependent, and it's theoretically a bit of an unexplored quagmire. Anyway, in the context of a circular cluster orbit, you have an effective potential, which is just the potential pieces of that energy which I showed you before, cluster potential, combination of the galactic tide, and the centrifugal potential. And if you just look at the xy plane, then this is a two-dimensional potential, and you can map the potential well as the third dimension, and you can also map equipotentials in the xy plane, as I've done down the bottom here, rather crudely, unfortunately. But this is the potential well of your star cluster. And so the stars you imagine would fit in here. There are two saddles at the edge of this potential well, which correspond to singularities of this field of potentials here, and these correspond to the so-called Lagrange points of this problem. And these are often taken to be the points which mark the edge of the star cluster. And the reason for that is that there's a last closed equipotential which goes from one Lagrange point around this gap here to the other Lagrange point around here. And you can imagine that since this corresponds to the lowest point of this potential surface here at the saddle, that this is the place where stars would spill over from the interior of the cluster out into the galactic field and would measure the edge of the bound stars of the cluster. And again, that's not the case, even in a cluster which is moving on a circular orbit, a fact which is not very well known, and again is going to be the subject of one of our projects.
So this depends on whether it's foregrade, the star is foregrade or retrograde.
It depends on the center of
Factor of
rotation.
2, right? The time radius. Between foregrade and retrograde.
Well, you have to define what you mean by target.
So if there's a cluster rotating like this, okay, and now a star in the cluster rotates the other way around,
Yes.
inside the cluster.
Yeah.
Okay. Then its tidal radius is different than foregrade star in the same
Yes.
cluster, right? By factor of 2.
Well, I'm surprised you said a factor of 2, actually, because I thought it was goes to almost arbitrary time.
Okay.
So you can help supervise the project on this. Okay, these Lagrange points, I've mentioned this, it's the last closed component of the equipotential map. And certainly within the context of this model, and this is true in Heggie's understanding of this situation as well, stars which do have energy below the value of the potential at the Lagrange points must remain inside the star cluster forever if the cluster potential is time independent. The distance of the Lagrange points from the center of the star cluster is often assumed to be the limiting radius of the star cluster if you apply a model like the King model, for example. And so in King models where the cluster members are confined to energies less than 0, the sphere in which the potential is equal to 0 is usually taken to be the sphere of radius equal to the tidal radius in this set. These Lagrange points being singularities of the effective potential, they're actually equilibria of the equations of motion, which are derived in the last picture. And this calculation here, in which I'm computing the position of one of these equilibria, so I'm just equating this term here with this term here for a point mass, for an isothermal galaxy. The formula for the position of the Lagrange radius is given by this formula here. If you approximate the cluster potential as that of a point mass, as you're well outside the bulk of the mass of the cluster. And so you get this formula for the tidal radius in terms of the 1/3 power of this ratio here, which is equivalent to what Doug was talking about in terms of the 1/3 power of the mass times the distance from the sun as being the total radius for time problems. By the way, if there's somebody here who's doing a PhD and there's any danger that I'll be your PhD examiner, a quick derivation of this formula is one which I ask every single PhD examination candidate that I have to examine. So
I can vouch for it. He also handed me 7 pages of paper.
it's the only time I ever had the upper hand in the matter. Here it is. PhD examination. Okay. Self-consistent model with a tidal field. Virtually every model of a star cluster which gets fitted to a star cluster ignores the galactic time on the stars inside the star cluster. Okay, there's an outer boundary which is determined by the tidal field, but that tidal field is still acting in the stars even when they're inside the star cluster. And there's really only one set of models which account for that, which are these ones. I was a student, a postdoc, did an example of that a long time ago, and Annalisa and that team came along and generalized it a bit more recently, that there's more care and more exactness. So it's again basically using this king-like formula here, except instead of using the king form of the energy, I'm using a sort of jackety form of the energy without factor of -2. This is again a tricky problem to do because the cluster is inherently triaxial. And that was my first escapade into triaxial stellar system. Well, I guess I'm getting on fairly well through here, but I'm unfortunately getting on now to areas which I'm even less familiar with. I mean, snapshot modeling is not my thing, really, but it is important, and it lies at the heart of a lot of what people do. But the kinds of parameterized models like King and Ritchie King and so on, which I've been discussing so far, are not the only kinds of ways of trying to fit basically the solutions of the collision-Boltzmann equation to the observations of the star cluster. And there's Jeans modeling, which again one can find the theoretical basis of this in Binney and Tremaine, which in summary is simply a matter of taking the velocity moments of the collision-Boltzmann equation, the time-independent collision-Boltzmann equation, because there's no deep term here, and then you average over the velocities, making appropriate assumptions about the distribution function f. For example, if you just have a look at the various components of this term here,